Welcome back to the Math Professors. If you enjoy content that can be found in any college math class, please consider liking, subscribing, and sharing. I'm Professor Ed Hamlin, and I'm going to cover evaluating a mixed composition of trig and inverse trig functions. So we're going to start out with a composition that's not mixed, say the sine of the sine inverse of a half. And really this is going to give us a way to be able to do some more complicated ones. So as long as I'm inside the restriction, then I know that the function and the inverse are going to cancel. So we're just going to get equal to a half. And I know that the sine inverse is defined from -1 to +1 because those are really the outputs of the regular sine function. So this is going to give us 1/2 back. Now, if I want to find this value here, this is the sine of the cosine inverse. These things are mixed. They're not the same thing, so they're not going to cancel. So if I look at the unit circle, what I know is that 2 pi over 3, I'm going to get, a x coordinate of a half, and this is going to be, root 3 over 2 for its y. Now, so if I want to find, this thing's value, this is going to be the sine of the cosine inverse of -1/2, and remember that, the cosine inverse is defined up here. So the cosine inverse of -1/2 is going to be equal to this angle, which is going to be equal to 2 pi over 3, and then finally the sine of 2 pi over 3 is going to be equal to root 3 over 2. Now another way I want to do this is I would prefer to try to write the sine of the cosine inverse of this -1/2 into, say, the sine of the sine inverse of something. So what I'm trying to do is I'm trying to find a value for which the cosine inverse gives you the same value as basically the sine inverse. And what I need is the cosine inverse of -1/2 gives us this coordinate of -1. Now the sine inverse is a little more complicated. It's over here. But I know that this angle right here is also going to give us exactly the same thing for the y coordinate, which happens to be equal to pi over 3. So this would be the sine of the sine inverse of root 3 over 2, which has the exact same y coordinate. So this again is going to be equal to I know it's technically different. This would be the sine of, well, the sine inverse of root 3 over 2 is actually going to be equal to pi over 3. But the sine of pi over 3 is equal to, the y coordinate, which is going to be equal to root 3 over 2. But that's kind of a little bit redundant. What I'm trying to show you is if I can give you the same output, that the sine of the sine inverse of this number is going to be just itself. I know I'm hopping around the circle, but our real goal is to be able to show that. Now, there's another way to do that. So let's kind of do B again, and we're going to do this in such a way that I'm going to use the Pythagorean theorem to show this, which is going to allow us to do this for all angles. So if I want to say what is the sine of the cosine inverse of, say, -1/2. So the way we do this is I want to write this as the sine of the sine inverse of the some value here. Now I don't want to hop around the unit circle by using triangles. I'd rather use triangles through the Pythagorean theorem. And in order to do that, well, let me kind of give you some a strategy here. So what I want to do is I want to turn a cosine inverse into a sine inverse. Now, we can't do that directly, but I can turn a cosine value into a sine value using the Pythagorean theorem. So what I'm going to do is I'm going to call this basically the sine of some angle theta. So what that would mean is that theta is equal to the cosine inverse of this -1/2. Now, I can't turn a cosine inverse directly into a sine inverse, but I can turn cosines into sines. So again, I'm just calling this piece here theta. Now, once I have the cosine inverse of -1/2 is equal to theta, I can rewrite this as a cosine function. Now, when you go from a function to inverse, it switches the input and output. So this is going to be equal to -1/2, and this is going to be equal to theta. Now we can use the Pythagorean theorem. The sine squared of theta plus the cosine squared of theta is equal to 1. And the cosine of theta is going to be equal to 1/2, so negative 1/2. So this is the cosine squared, and we still have the sine squared of theta. Now I'm just going to isolate the sine. So first we square the sine squared of theta plus 1/4 is equal to 1. So the sine squared of theta is going to be equal to 1 minus 1/4, which is 3/4. So finally, the sine of theta is going to be equal to plus or minus the square root of 3 over 4. Now, since we're talking about, eventually our sine inverse, but since we're talking about the cosine inverse of this negative 1/2, what I already know is that cosine inverse is going to live on the top half of the circle, and the sine function is the y-coordinate, so that means the y-coordinate has to be positive since we're on the top of the circle. So really that means that this is going to be positive, the square root of 3, and the square root of 4 is equal to 2. So now that I know that the sine of theta is equal to root 3 over 2, which is kind of what we showed here, right? Then I know that I can rewrite this as it's, I technically have my answer. This is the sine of theta, so the answer is root 3 over 2 as we showed, but what's kind of fun is to turn it back now. So now if I want to write this as a sine inverse, your root 3 over 2 is going to go here, and then your theta is going to go here, so we can put it that way, which means that the cosine inverse of negative 1/2, like we said, was the same thing as the sine inverse of root 3 over 2. So now this original expression, our solution was the sine of the cosine inverse of negative 1/2, but this piece here is equal to this, so this is going to be equal to the sine of the sine inverse of root 3 over 2. And since this is under the correct restriction, those things annihilate, so we just get our root 3 over 2. All right, you might ask why we went through all that work. Well, if we don't have these nice numbers that are on our unit circle, we can't just kind of click back and forth between our angles. What happens if I ask for the sine of the cosine inverse of maybe 3 over 5 or something like that? Something that, those numbers don't live as coordinates on the unit circle, at least the ones that you have memorized. So let's maybe do two more. One where there, you don't see them on your common unit circle, and then we'll also switch them maybe at the third function. So what is the cosine of the sine inverse of negative 5 over 13? Now I don't see that on the coordinates of our printed unit circle. So what I'm going to do is I'm going to call this inside piece theta. Again, the reason why I do this is I can't turn a sine inverse directly into a cosine inverse. But if I turn this into a sine, I can turn the sine into a sine inverse. So if I write this as sine, then, input and output switch. And now I can use the Pythagorean theorem to turn this sine function into a cosine function. So the sine of theta is equal to minus 5 over 13. So we're going to have to square that, plus cosine squared of theta is equal to 1. So this is going to be 25 over 169 plus cosine squared of theta is equal to 1. So cosine squared of theta is going to be equal to 169 minus 25, which is going to be 144 over 169. And then finally we're going to square root. Now this would be plus or minus, well, the square root of this thing, which we know we're going to get 12 over 13, but the question is it positive or negative? Now, right now, I in my unit circle, we're talking about we went from sine inverse to sine, which forces us to be over here because the sine inverse is on the right half of the circle. And what I know is on the right half of the circle, the cosines are the axis coordinates. So over here, all the x's are positive. So this is indeed positive 12 over 13. Now remember, this is the cosine of theta, so this is technically your answer. You're welcome to stop here, but I like to rewrite this. So if the cosine of theta is equal to 12 over 13, then that means the cosine inverse of 12 over 13 is equal to theta, which means that these two pieces are the same. These are equal because they are both equal to theta. So I can rewrite this as the cosine of, this thing, the cosine inverse of 12 over 13. And since this is, in between negative 1 and positive 1, it's under the restriction, so the inverses will and the function will annihilate to give us our answer. Again, once you have this as the cosine of theta, clearly that was your answer, so you're technically done. So one last one. Let's do maybe a tangent function, and that will be it. All right, so let's do this. What I want, again, is I would like the tangent of the tangent inverse, but unfortunately I have the tangent of the cosecant inverse. So the first thing I'm going to do is I'm going to call this cosecant. It's an inverse trig function, so it's equal to some angle. So then I can, I can turn this into the regular cosecant. It means the angle and the input are going to flip. Now, I don't want to use the cosecant. I prefer to use the sine, so I can turn this into a sine. So I know that the sine of theta is going to be the reciprocal of the cosecant of theta, which is 5 over 3. Once I know the sine of theta, I can also find the cosine of theta. And when I know the sine and the cosine, I also know the tangent. So that means the sine squared of theta plus cosine squared of theta is equal to 1. So this is going to be 3/5 squared plus cosine squared of theta is equal to 1. So this is 9 over 25 plus cosine squared of theta is equal to 1. So cosine squared of theta is going to be 25 minus 9 is going to be 16 over 25. The cosecant is the reciprocal of the sine, so they're going to have the same restrictions, which means we're going to be on the right side of the circle, which means all the cosines will be positive because cosines are the x-coordinates. So that means the cosine of theta is going to be plus or minus, well, technically plus the square root of this thing, which is going to be 4 over 5. Now that I know the sine of theta, I know the cosine of theta, I now know the tangent of theta. And remember, that's what this is. This is the tangent of theta. So once you know the tangent of theta, this thing will actually be your answer, but I still like to turn it into inverses and then kind of show that inverse property. So this is going to be, the sine of theta over the cosine of theta, and the sine of theta being, 3 over 5, the cosine theta being 4 over 5. And when you multiply by the reciprocals, you can see those 5's will cancel, so this will be equal to 3 over 4. So this technically is our answer. But again, I like to show all the things. So that means the tangent inverse of 3 over 4 is equal to theta, which means that the cosine inverse of 5 over 3 is equal to the tangent inverse of 3 over 4. So that means I can rewrite this as, our tangent of the cosecant inverse of 5 over 3 as the tangent of, the tangent inverse of 3 over 4. And since this is underneath the restriction, tangent inverse goes from minus infinity to infinity, so this is clearly under the restriction, so this is going to be straight up 3 over 4. As we said, this was always going to be your answer in the first place. So what I love about this is like the perfect capstone for the end of like a trig class. What you have is you have inverse trig functions. You have changing from an inverse to a regular function, so you're flipping inputs and outputs. You have to be concerned about restrictions. You have to use the Pythagorean theorem so you can turn a sine function into a cosine function. From there, you have to know your what the tangent is, and it's the reciprocal of the sine over the cosine function. And then finally, now that you have the tangent function, you can turn it back into its inverse by doing, again, flipping input and output. And then finally, the composition of a function in an inverse is that input as long as you're underneath the correct restriction, in which you are. So this really encompasses all the things that you would see like in a trig course all in one problem. So if you like the content, please subscribe.